Hi physics students, so this video is a resource for you to study. This will be solutions to a number of fairly difficult problems, some of which we looked at this week in preparation for the final. But just to kind of give you a good mix of sort of harder problems to study from. And so this will have the solutions all in one place. So the first question is a Newton's law question, Newton's laws. And so this one incorporates friction. So we encountered this basically in the beginning of chapter 5. And the question says we have a 3 kilogram block sitting on top of a 5 kilogram block, which is on a surface. And the 5 kilogram block is pulled to the right with a force F as drawn in the figure. And we're given the coefficient of static friction and the coefficient of kinetic friction. And the question is, what is the minimum value of F needed to move the two blocks? And if the force is greater than that minimum by 10%, what is the acceleration of the blocks? So I chose this question because this gives us a good opportunity to practice with our summing forces and doing free body diagrams. And so that's where we're going to start. Let's label these as M1 and M2. And where we would start with this is let's do free body diagrams for each block, and then we'll sum the forces, and then we'll see if we can figure out what the minimum force and the acceleration would be. So for M1, what all forces do we have? Well, we're going to have its weight down. We would have the normal force. I'll call that Fn1. We also have tension force. It's pulling it to the left. And then we would also have, a force of friction. Let's call this F friction 1. So that's M1. M2, a little more complicated. So again, we would have M2's weight. We're going to have the normal force on M2. Again, we would have force of tension also to the left. Oh, I should mention too, we have our coordinate system. What else? We're going to have some other ones. So we would have the applied F to the right. Now, additionally, we would have a force of friction between the 5 kilogram block and the surface. Let's call this one F2. Now, we would also have the force of friction FF1. So if FF1 is pointing to the right on the top block, that means it must be pointing to the left on the bottom block. Example of Newton's third law, where we'll have equal but opposite forces acting on those two blocks. And then we have one other one. We have also the weight of the top block down on top of the bottom block. And I think that's all of our forces. And so notice this is fairly complicated. We have a lot of forces to keep track of. So what's our next step? Let's sum the forces. Let's look at M1, and then we'll look at M2. So the sum of the forces in the y direction, we would just have Fn1 minus M1g. That's going to, in general, sum to MAY, but that'll be 0 because it's not accelerating in the y direction. So in other words, Fn1 is just equal to the weight. We sum the forces in x. What do we have? We're going to have the force of friction 1 is in the positive x direction. The tension force is going to be in the negative direction. And x direction. And if we assume that this thing is accelerating to the left, that would mean that this would be equal to m1 times negative a. Okay. All right. Let's look at m2. So if we sum the forces in y, we're going to have, what all do we have? Normal force 2 is pointing up. m1g, m2g are both pointing down. This will equal 0. And so this is just telling us that the normal force is going to be equal to the weight of both blocks, which makes sense. The normal force is preventing the combination from, accelerating in the y direction. And if we look at the sum of the forces in x, we have a fair number to keep track of here. We have the applied force F. We have minus a factor of F1 minus F2 minus the force of tension. And that's going to equal m2 times the acceleration in the x direction, which I'll just call a, because recognizing that since the blocks m1 and m2 are connected, they have the same acceleration if they're moving together. Okay, so I think that's all of our forces in x and y on each. So notice we basically have two expressions. What are we looking for again? We're looking for the minimum force that's going to be required to get this thing to accelerate. So let's find an expression for the acceleration, and then we can see what will cause that to be more than 0. So notice we have basically two things that are unknown in two equations. We have, not F is unknown, rather. We have A, and we have the tension appearing in both of these expressions. So how about we substitute equation 1 into equation 2 here so as to eliminate the tension. So from 1, we can see that the tension is equal to negative m1a, positive m1a rather, plus f1. And then we can substitute that into this expression, into 2. Let's give ourselves a little more space here. If we substitute that into 2, we will have f minus ff1 minus ff2 minus m1a plus ff1 equals m2a. We can put everything that has a in it on one side. Notice we'll have a times m1 plus m2 is going to be equal to, let's see, we'll have f minus, notice we have two factors of ff1, so minus 2 ff1 minus force of friction 2 ff2, and I think that's everything. And so we can then, divide by the sum of the masses and get an expression for the acceleration. The acceleration is equal to f minus 2ff1 minus ff2 over m1 plus m2. Now we can put in what the force of friction is equal to. So recall that the force of friction in general is equal to the normal force times the coefficient of friction. So what that means is that FF1 would equal the normal force times, or the normal force on 1 times the coefficient of friction, so mu times m1g, and FF2 would equal mu times the normal force on 2, which was m1 plus m2 times g. So we can put those pieces in. Let's see here. Get a little more space here. So this will be F minus 2 times mu, we're talking about the static friction case first, times m1g minus mu times m1 plus m2g, all over the sum of the masses. And notice there's a factor of mu s m1g, and there's an additional factor of mu m1g here. So we can combine these together. We can simplify this a little bit further. F minus 3 mu s m1g minus mu s. You could imagine organizing this differently, solving this differently, but this is sort of a fairly concise expression for the acceleration. And recall the first part of the question asked us for when, what would the applied force have to be for this to accelerate. And that's a way of saying that F would have to be larger than this stuff. So the critical condition would be for F to be larger or equal to negative, the rest of the stuff that's in the into the numerator. So we can solve for when those are equal, and that'll give us the critical force. And so then we just put in our numerical values. 3 kilograms, 3 times mu s 0.6 times mass 1 was 3, 9.8 plus 0.6 times 5 times 9.8. Multiply that together, and we'll find that the force minimum would be, let me see what the number is here. Uh, 82 newtons. So that would be the minimum force that would be required to get the thing to move. And then the second part of the question, recall, asked us to find the acceleration when it started to move, and for a force that would be 10% larger than that. So we could plug that in. The acceleration, 110% F, would be 82 times 1.1 for 10% larger, minus, all of this same stuff. So, and now instead of mu s, we would use mu k because it's moving, so we would need the coefficient of kinetic friction. So 3 times 0.4 times, what was the mass? 3 kilograms times factor of g. So you see here, just putting in our ingredients, divide by the sum of the masses, and we would find that the acceleration for 110% F would be 4.5 meters per second squared. So this is a pretty good question in that it allows us to do fairly complicated free body diagrams. We need to do some algebra to find an expression for the acceleration. And then we looked at a condition, what would be the minimum force to get it to move, and what would be the acceleration given, particular applied force, 110% of that minimum, and, noting also that when it starts to move, mu s goes to mu k. So this is a pretty good question in terms of looking at Newton's laws, and a good one to review. Okay, so this next question gives us a chance to look at energy conservation as well as centripetal acceleration. So this is a good one for review as well, as it combines kind of a couple different concepts that you're responsible for on the final. So first part of this question, so basically the setup here is you have a ball that's on a string, and it's held horizontally, and then you drop it, and it swings down, and it's going to, we're wondering what the velocity is at the bottom. That's what it's asking for part A. We're also wondering, what the velocity is going to be here. That's the second part of the question. Part B is asking, v here. Let's call it v2, say. And then the last part of this question is asking, what's going to be the tension in the cord, basically immediately before and immediately after it strikes the peg. So, it's going like this. It's going to hit this peg. And we're curious about, what's the tension before, and then what's going to be the tension after it hits. Okay. Kind of in those two scenarios, right when it's getting to the bottom. So for part A, there's, we could, in general, you could solve this with forces or whatever, but energy conservation is really a good way to approach this, because notice the tension force is going to change depending on how high you are. So it makes it a lot easier to approach this from energy conservation. That's kind of why I have that mentioned at the top. So basically, we're not worried about friction in this situation. So it's a conservation of mechanical energy. Mechanical energy initial is going to equal the mechanical energy final. And we're free to choose where to put our coordinate system. And so let's pick the bottom. It's a convenient choice because it won't have any height. So that means that, let's call this A, B, C. So that means the potential energy at A plus the kinetic energy at A is going to equal potential energy B plus kinetic energy at B. And at the top, it has no kinetic energy because it's dropped. It's released. And then at B, it will have no potential energy because it's at y equals 0. And so we're just going from potential to kinetic. So, and what is the potential energy but mgh, where h is going to be the full length, mgl. For this question, that's going to go into 1/2 mv squared. Notice the mass is going to cancel, and we're left with this part as being v is the square root of 2gl. Okay. Part B is telling us there's this peg. So this is sort of just a geometry situation. We're really interested in then what would the speed be at this height. We could call, maybe if this is, if this is 0.2, that would mean that this is 0.4 L. And this would be 0.6 L. So it's the same kind of situation. We can do conservation of energy. Now the potential energy at A plus kinetic energy at A is going to equal potential energy. Now we've gone through the bottom and we're back up to C plus kinetic energy at C. And we don't even have to solve for what's happening at B. You know, we don't have to set B equal to C. We can set A equal to C because since there's energy conserved, it's going to be the same. And then again, so this will be 0. And the potential energy at C is not going to be 0 this time because it has some height relative to where we have put our coordinate system. So let's put in the pieces here. This would be mgl is going to equal the potential energy at C now relative to the bottom is mg 0.4L, and that's going to equal, or that's going to have added to it 1/2 mv squared. Now notice again, the mass is going to cancel, and if we're solving again for v, we would have this gl minus 0.4 gl, so we'd have 0.6 gl equals 1/2 v squared, and then we could solve again for v, and it's going to be the square root of 0.6 times 2gl. So in other words, this is the square root of 0.6 times 2gl, which is what we had before. So this 0.6, square root of 0.6, is going to be less than 1. And so the v at C, or V2, or whatever we called it, is going to be less than the v at the bottom, which makes sense. The other thing I would point out to you is, you could pick your coordinate system to have its origin here. And then notice what would happen is that you would just go immediately from MGL. The initial potential energy would be, instead of MGL, it would be MGL times 0.6 L, because that's the height. And so it would make it simpler, but it works out the same because we haven't changed the behavior. We've just, it's just a product of where you put your coordinate system. So this was part A, the speed at the bottom. This is part B. And then the last part of the question is asking us about the tension. And so this connects back to what we have done with forces. So consider at the bottom, you have the weight pulling down and the tension pulling up. And then notice, since this thing is going sideways, it's going to have a velocity, and it's also going to have a centripetal acceleration by virtue of the fact that it is going in a circle. And so when we sum the forces in R, what do we have? We have the tension pointed up minus the weight is going to equal the mass times the centripetal acceleration. The tension minus the weight is going to equal mv squared over r. Now I would note too, this is not strictly correct because this thing is also accelerating at the bottom. So I would just note, when we had introduced this, we were talking about constant speed for an object that's spinning, but it'll work well enough for us to do this. So this gives us a way to compute the tension in terms of the weight and the radius and the speed. And so we have mv squared over r times mg, or maybe we could consolidate this down a little bit, and it would be m v squared over r plus g. And we could try this for these two different cases. So immediately before it strikes the peg, the radius is L, in which case the tension, oh, and we have V as well. So 2GL square root squared over L plus G. So notice this is going to become 2GL over L. And so we have 2G plus G. This will become 3mg, so 3 times the weight before it hits the peg. And then after, give ourselves a little more room here. Try and keep the picture on there still. After, R becomes much less. It's only 0.2 L. In which case, this tension then would become, so the speed hasn't really changed yet because it's still at the bottom. So notice, again, the factor of L would drop out, and we'd be left with 2GL over 0.2, or 2G rather, over 0.2, which is actually 10, plus a factor of G. So this would become 11 mg. And this might agree with our intuition. Once this thing hits the peg, it has a much shorter radius, so the tension is going to go way up because a part of that tension depends on v squared over r. So v hasn't really changed, but r has gotten a lot smaller, so the tension would go up. So this is before the peg, after. And that's just another little good thing to review. Basically, this relationship between the centripetal acceleration and v squared over r was something that we made a lot of use of. And looking at Newton's laws in, and when talking about circular motion. So our third review problem is a quick gravity problem. Students had been asking about looking at gravity problems, and I thought this was a good one for us to look at. So this question is asking about the Apollo command module in orbit around the moon. So we have the moon, and the command module would be in orbit around that. Ooh, if I can draw a circle. Oh man, you get the idea. It's some height. So we have the radius of the moon, and the radius that we would care about would be the radius of the moon plus that height. And this would have some speed v, and there would be a centripetal acceleration that would be pointed towards the center. And in this case, it is, of course, the force of gravity that's providing that. And kind of the starting point for most all of these problems is the mass of the moon times the mass of Apollo over r squared is going to be equal to the mass times the centripetal acceleration, so really, let me back up a second. We look at the sum of the forces in r, and notice that that would be equal to the mass times the centripetal acceleration. The force that we're looking at is gravity, and so this would equal mv squared over r. Notice the mass of the spacecraft would drop out, and we lose a factor of r as well. And so we have gmm over r equals v squared over r, or rather v squared. And the other piece of information that we need is that we need to connect this to the period. Well, 2 pi r divided by the period will give you the speed. So 2 pi r over t, i.e. how long a circumference of an orbit is, divided by the time per orbit is equal to the speed in the orbit. And so we can put that in here. Mass of the moon over r is going to equal 2 pi r over t squared. And then we can solve this for the period. So if we shuffle stuff around, this would be 4 pi squared r cubed over gm. And then we would have to take a square root of that whole thing. If we put in our numbers, the mass of the moon, sorry, the radius of the moon would be or radius of the orbit rather. Again, the radius of the moon plus the height. That thing cubed divided by g, gravitational constant, 7 times 10 to the minus 11. And also, what else do we have in there? The mass of the moon. So put all those ingredients together, take a square root, we would find that the period is equal to about 7,000 seconds. You divide by 3,600 seconds, i.e. The amount of seconds in an hour, you would find that this is very close to 2 hours. And so that was part A. Part B asks us to just calculate the magnitude of the gravitational force between those. And so notice in this case we would need, so this is actually the magnitude of the force of gravity, which is given by gm, mass of the moon, mass of Apollo, over r squared, 6.67, just 10 to the minus 11 times, now we need the masses, again, over r squared, where our r is again the height plus the radius. And, crunch those numbers, you would find that this force is something like 40,000 newtons. The fourth question that we have is momentum conservation, and it's actually a pretty complicated question. After I had looked at this one, I don't think I would give you something that's quite this complicated on an exam just because the algebra is involved enough. But I think it's good for you to see, maybe I would ask you to set something like this up, for example. And I'll give you the whole solution so you can have it for your reference. So this question asks us to consider bowling. You have a bowling ball that strikes a pin and the pin goes off at an angle. And we're told what the initial speed of the ball is. And we're also told that the mass of the ball is 5 times the mass of a pin. And we're given, the angle here that the pin is deflected at. And we're also told that this is going to be an elastic collision. So it's not necessarily realistic, but it makes this problem tractable. You know that with macroscopic objects, there's going to be some energy that's going into, deformation of those objects, but we're going to assume that this is elastic. And we want to find the speed of the pin. We want to find the speed of the ball. And we want to find this angle theta. All right. So let's set up our momentum and energy conservation questions. So since it's elastic, we'll also have energy conservation. And see what we have as our starting point. So first thing is energy conservation. We know that the initial kinetic energy, so 1/2, let me write this as capital M, v naught squared, is going to equal 1/2, so this is, or maybe I'll put a B here, mass of the ball times its, I'll call it v final squared, plus 1/2 little m, mass of the pin, times v final pin. Let me call this v final pin, v final pin squared. So this is one equation. The kinetic energy initial of the ball is going to equal the kinetic energy of the ball after the collision plus the kinetic energy of the pin after the collision. Just try and be kind of neat here. So that's one. Then we can look at momentum conservation. Let's look at the momentum in x first. How about? So the initial momentum in x is going to equal the final momentum in x. Actually, since we have them as components, let's leave it like that. And so what do we have? Well, the initial momentum in x is nothing. The ball isn't moving in x. So this is going to equal the final momentum in x. The final momentum in x that we have, and actually neglected to put our coordinate system on here. So the final momentum in x we have is going to be the mass of the ball, the mass of the pin, times v final of the pin, times the component that would give us the x component, which is going to be cosine theta. Or no, not cosine theta, sine theta. Actually, sine of 75. Theta is our unknown angle. So that's the component of momentum from the pin that's in the x direction, and it's positive because it's pointed to the right. And then we would also have, and this chunk will be negative because it's pointed to the left according to our coordinate system, we would have the mass of the ball. Try and draw this big M to indicate the more massive ball, times v final times sine of theta, so our unknown angle. And those sum to 0 because the initial momentum was 0. And this would be our second equation that we're working with. And then let's look at the momentum conservation in y. So sum of the momentum in y initial is going to equal the sum of the momentum y in final. So in y initial, we have the mass of the ball times v naught. It's all in y. And that's going to equal what? Well, we'll have the mass of the pin, v final pin, cosine of 75 degrees. So that's the component of the pin momentum that's pointed in the y direction after the collision. And then additionally, we would have the mass of the ball, v final, times cosine of theta. And that's the component of the ball's final momentum that's pointed in the y direction. So notice we have 3 equations and we have 3 unknowns. We don't know theta. We don't know the final velocity of the ball. and we don't know the final velocity of the pin. 3 equations, 3 unknowns, rather complicated. So, how to approach this? There's, of course, a lot of different ways that you could approach this. We basically need to eliminate some stuff so that we can solve for these parts. So, one way that we can, one thing you might find with these questions is it's hard dealing with the angles. So why don't we try and eliminate theta? And one way to eliminate theta would be to make use of the fact that sine theta squared plus cosine theta squared equals 1. So what we can do, and this is going to be our game plan for our algebra here, is we're going to combine equation 2 and 3 and square the sine theta and cosine theta pieces so that when we add them together, the theta cancels. And then we can substitute that in to equation 1. So basically here's going to be our game plan. Combine 2 and 3, sub into 1. So in other words, let's write, so from 2, mb v final sine theta is equal to mp v final, the pin, sine 75. So this is from 2. From 1, mb v final cosine theta, or sorry, rather from 3, is equal to mb v naught minus mp vfp cosine 75. So this is from 3. And then let's square both of those. So mb v final sine theta squared plus mb vf cosine theta squared. So we're combining 2 and 3 is going to equal mp vfp sine 75 squared plus this thing squared, mb v naught minus mp vfp cosine 75 quantity squared. And then notice that that will equal this sine theta and the cosine theta we can factor out. So let's write it like this, mb vf squared times cosine squared theta plus sine squared theta. So we've just factored out the factor of mb vf. And then this becomes 1. So just to rewrite it here, we would have, what we have so far is mb vf squared equals, maybe I can just copy this here, this bit. This is kind of a nice intermediate step because we have eliminated theta. Okay. So I think I mentioned to you this to you before. I mean, the algebra with these can get kind of complicated. It's simple enough to state our equations for momentum and energy conservation, but the algebra can get rather can get kind of long. So what do we do now? We have something that's MBF final squared is equal to our other stuff. Let's substitute in for this into 1, and that'll let us eliminate V final and then solve for VB final. So sub in, FP, solve for VFP rather. So sub into 1, solve for VFP. So let's do that. It's over a little bit. So notice from 1, I would have 1/2 mass of the ball V0 squared. That's going to equal 1/2. So actually, we can sub in this whole thing at mass of the ball times V final squared. Notice we'll have to divide by a factor of mass of the ball, and then multiply by MB V final squared. And what is MB V final squared but this whole thing? Should be able to just paste that again. Oops. Come on. Try and do this as concisely as I can manage. Whoops. Try this again. Technical difficulties here. All right, so we can stick that in there. And notice we would just have this other factor of 1/2 mass of the pin, V final pin squared. So that's a pretty nasty looking expression, but notice it does not contain anything that we don't know except for the V final pin. So we can solve this for V final pin. Okay, and so at this point, this is a good point to notice that the mass of the ball is equal to 5 times the mass of the pin. So we can start to substitute that piece of information in, and that'll let us cancel some stuff. So this would be, I'm just going to say the mass of the ball is 5 times the mass. So 1/2 times 5 times the mass. V0 squared is going to equal 1/2, where little m is the mass of the pin. So 1/5m. And then now we have, this big thing. M VFP sine 75 plus, and this thing is squared yet, V0, oops, so MB becomes 5M. Then this is mass of the pin, VFP cosine 75 plus 1/2 M V final pin squared. So, okay, we're starting to make some progress. So let's now expand these, FOIL out this term that has the difference of pieces, and see if we can kind of cancel some stuff out. This would be the part of this where you would fast forward, because it's just me doing algebra and kind of boring. So if we expand this out, what would we have? We'd have 25 m squared V0 squared minus 2 times, the product of those pieces. So this would be minus 10 m squared V0 VFP cosine 75, and then plus m squared VFP squared cosine squared 75, and then plus our 1/2 m VFP squared. So this looks pretty gross, but really we have everything expanded, and a bunch of this stuff is going to cancel out here if we stare at it a little bit. So first off, notice we can cancel. This factor of 1/2 appears everywhere. We can actually cancel the factor of m as well, because this has got a factor of m. This has m squared over m. All of these pieces do. So the m's all go away. And then we can, well, let me just rewrite it, and then we can we will combine this piece and this piece, the v final pin sine 75 squared thing can combine with this one, the cosine squared piece. So let me consolidate this stuff. So we have 5 v naught squared is going to equal 1/5 VFP squared. So the sine squared 75 plus the cosine squared 75 is going to give us 1. And then what else do we have left over? We have 25 v naught squared minus 10 v naught VFP cosine 75 plus our VFP squared. So this becomes 1, and notice we have 5 v naught squared and 25/5 v naught squared. Those are going to go away. We have, let's multiply through by the 5. So this would become 1. This would have a factor of 5. If we multiply through by a factor of 5 to cancel out the 1/5. And we can combine then this VFP and 5 VFP. So we would notice this is 0 is going to equal 6 VFP squared minus 10 v naught VFP cosine 75. Notice we can cancel a factor of VFP as well, and it's really consolidating down to VFP is going to equal 10 v naught cosine 75 over 6. So all of that work to boil down to solve for, we end up with a little expression for the final velocity of the pin, and we can put our numbers in here and find that VFP is going to be 10 times 13 times cosine 75 over 6. We get 5.6 meters per second equals the speed of the pin. All right. What about theta? A lot of algebra. We just found this. What about theta, and what about the final speed of the ball? Well, we can use our equation 1. Now that we know let me just state it again. Now that we know v final pin, we can cancel out our factor of 1/2 that appears here. Note that this is actually 5 times m for both of these. Now we know v naught, we know v final pin, so we can solve this for v final. So let's see, what is v final going to give us? Well, let me do it in a couple steps here. MB v final squared, and let's divide out by a factor of 5. So we would have m vf final squared is going to equal m v naught squared minus m v final pin squared over 5. And then that means that oh, we can also cancel out the m, of course. So v final is just going to equal the square root of v naught squared minus v final pin squared over 5. We plug those numbers in. 13 squared minus 5.6 squared over 5 gives us 12.76 meters per second. So that's v final for the ball. And then the last ingredient, this was part A, part B. The last bit was asking us to find the angle theta, so we can use one of our other expressions. VFP, so we can use our x momentum expression, for example. Now that we know the speeds, we can put in the fact that m of the ball is 5m. That'll cancel the mass of the ball, or cancel out the mass, and then we would just solve this for theta. Sine theta is going to be VFP sine 75 divided by VF, sorry, 5VF, and take an arc sine. Find that theta would be about 4.9 degrees. So obviously this ends up being a pretty complicated problem because we have 3 unknowns, but I think it's good for you to see kind of a gory problem like this. I can't really ask you to do something as complicated as this on the exam because it would take too long, but I might ask you to set something up like this where you have momentum conservation in x and y and also energy conservation, or I might ask you, simpler versions of this where you don't have as many variables. The procedure is the same. You set up your equations for momentum conservation, for energy conservation. You're going to do algebra to solve them. So hopefully this one is a good reference for you to have for a sort of more complicated momentum conservation question. So this last question that we had in the mix is torque and rotational motion. And so let's, this is sort of the freshest topic that we've been working with, so it would be good, I think, to have a question on this for your reference. So this consists of a roll of paper that has some radius, 7.6 centimeters. It says some radius. And there's a force you're pulling basically on the end of the paper, and it has some given moment of inertia and a given force. And you pull on it for 1.3 seconds, and it unrolls the paper. And there's also a constant frictional torque. Think of this as a torque that's resisting the pulling. So maybe there's friction in the roll or whatever. And assuming that the R doesn't change, i.e. the paper's thickness we can omit, we want to figure out the length that the paper unrolls, and we want to figure out in the time that you're applying the force, so in that 1.3 seconds, how much does it unroll? And then that frictional torque is going to continue after you've spun it up to speed, so we want to figure out how long is it going to continue to roll as it slows down and comes to a stop. All right, so basically, you're going to spin it up, and then it's going to spin down, and we want to figure out how much it unrolls during that whole situation. So the starting point for this is the rotational version of Newton's second law. Sum of the torques is going to equal I alpha. Now, we have 2 contributions to the torque. We have the frictional torque and also the applied force torque. And so this one is easy. The applied piece is easy because it's perpendicular on a roll like that. So this would be the force applied times R. The frictional torque is going to be negative because it's going to oppose that. And that is going to equal I alpha, and we're given what I is.
So we can put those ingredients together. This is 0.076. Force is 2.5 newtons. Minus this 0.11 meters times newtons, all divided by 3.3 times 10 to the minus third, our moment of inertia. We put those pieces together, we find that alpha would be 24.4 radians per second squared. So we have alpha. Now, if we have alpha, there's still a couple steps that we need to use to figure out how much it's going to unroll. So far we've made use of our torque relationships. Now we basically need to make use of our rotational kinematics to connect alpha to how far it unrolls. So if we look at our theta as a function of time expression, now that we have alpha, we can find theta, and if we have theta, we can find the length. So it starts from rest, so this will be 0. So basically, we can just put these ingredients together. And multiply by our time squared. So we're pulling on it, we're accelerating it for 1.3 seconds. We put those ingredients together, and we find that the amount of theta that it unrolls is about 20.5 radians. And then the last kind of connect the dots step would be, okay, if we know theta, so think of this as, you know theta, and we want to get this length L. The length is going to be r times theta, just like if the circumference would be 2 pi r, right, and that would be the entire way around. Well, a fraction of that would be theta times r. So we put these pieces together, 0.076 times our theta, 20.5 radians. We would find that the length that this unrolls is about 1.6 meters. So it's a fairly simple question, but we do have to sum the torques to find the angular acceleration, and then use that to find how much it unrolls in angle and how much that would correspond to in length. So that's part A. Part B asks us, so we want to know how much it unrolls after it's spun up. So this 1.3 seconds was, how much it took to accelerate it, and now we're looking after. So this is basically, accelerating, and this is winding down. So when we look at when it slows down, the sum of the torque, same starting point, sum of the torque is going to equal I alpha. But now the torque that we have is just the friction. And so if we solve this for alpha, it's just going to be the torque over I. Give ourselves a little more space here. And so when we crunch that, that's just going to be this negative 0.11 over. We find that alpha in this case is negative 33. So this is speeding up. This is when it's slowing down. Notice it's negative. Now it's kind of the same thing, except it's a little bit an extra wrinkle is that this would be slowing down from at a initial omega naught. So we need to know what that omega naught is, i.e. we need to know how fast it was going once we stopped accelerating it. We can get that from our other kinematics expression, where it originally started from rest, And so this would, you could think of this as like, the fastest omega that it got to would have been this 24.4 times our 1.3 seconds. And what would that be? 31.5. So that omega becomes the omega naught for part B for here. And then all we have to do is we can use our other kinematics expression, that omega final squared is omega naught squared plus 2 times this new alpha, maybe we'll call this, alpha 2 or something, times theta. So it has an initial speed now because it was going fast, but it's going to go to a speed of 0 because it's coming to a stop. So then we can just solve this for theta, which is going to be negative omega naught squared over 2 alpha naught, or alpha 2. So negative 31.5 squared over 2 times negative 33.3. So notice the negatives will cancel out. We get a positive theta as we expect. We crunch these numbers, we would find that this is about 15 radians. And 15 radians corresponds to less length. This is, if we do r times that 15 radians, we would find that the length 2 would be about 1.1 meters. So, yeah, fairly complicated question. It's allowing us to exercise our summing the torque to find alpha, but also, our various kinematics expressions for rotational motion, which I can actually, let me flag them here. We had, select the color, kind of to flag the different components that we use. We worked with sum of the torque equaling I alpha, but we also made use of, our kinematics expressions for rotational motion. So this is kind of a nice problem just to tie all those pieces together, and including even the fact that theta times r gives you the length. So hopefully this helps you as you study and get ready for the final.